All right, let's look at this question here. So we have monochromatic light. It's going to have a frequency of 5.50 times 10 to the 14 hertz. And it's directed through a diffraction grating with a spacing of 1.67 times 10 to the minus 4 meters. So we want to determine the distance between the third bright band or bright fringe and the fifth dark band or dark fringe of the interference pattern formed on a screen that is 2.50 meters from the grating. Assume the angle is small. So we're telling you this just to make life simple. The angle's small, use the small angle approximation. So the small angle approximation that we know and love, we have lambda equals xd over nl for bright fringes. And since we're dealing with dark fringes, we also want to have an equation for that. So where we have an n, we're just going to replace that with an n minus 1/2. Dark. So we have our equations. So let's sketch out what we're actually trying to ask in this question, because it's always nice to have like an actual interpretation of what's going on. So if I kind of look at my screen here, and again, this is a really, really rough sketch, so bear with me on this. So I'm going to say that this is my central maximum here. So here is my CM. And then I have this bright spot, this bright spot, this bright spot. I should be making this a bit more evenly spaced, but it is what it is. 1, 2, 3. So I want between the third bright and the fifth dark. Okay, 1, 2, 3, 4, 5. And we'll just assume the pattern kind of goes on. So for this, I'm going to have my third dark spot, 1, 2, 3 right here. So we're usually looking from the center of that. So that's my third dark spot. And then I want the distance between that, or sorry, the third bright spot and the fifth dark band. Oh, I should read these questions more carefully. Sorry, the third bright spot is going to be right here actually. So we're going to pretend I didn't make that mark. And I can't really erase it, so I'll just make this one bigger. And then the fifth dark spot. So I got 1, 2, 3, 4, 5. So there's my fifth dark spot. What I'm interested in finding is this distance here. Now, we might say, well, how the heck do we do that? Well, using our small angle equations, we know that the x value in this equation is the distance from the central maximum to the fringe in question. So for the third bright fringe, I have that distance from the center of the central maximum to this third bright fringe. I have x3. I'll put a little b for bright. And then I also know that if I use this equation for the fifth fringe, the dark one, I know that that'll be the distance between the central maximum and the fifth dark fringe. So x5, and then I'll put a little d just for dark. So I can calculate those distances using my equation. If I know these two distances, I know that that difference between these 2 points, it's going to be the difference between these two distances. So I can calculate these. Let's calculate those x values. So we're going to determine x3 bright and x5 dark. Don't mind my notation too much. All right, so for the third one, so for n equals 3, and then like I said, I'll put a little b for bright. So we have lambda equals xd over nl. What we would like is we would like to solve for x. So we know that x is going to be lambda nl over d. Now we're going to run into a little bit of an issue here. We know nl and d, however we don't know the wavelength. We're given the frequency instead. But this is an electromagnetic wave. So for an electromagnetic wave, we know that the speed of light is equal to the frequency times the wavelength. Or rather, the wavelength is just c over f. So what I'm going to do, you could calculate this in advance. Like you could do c divided by f to get a wavelength. I'm just going to sub this into here. It's what I want to do, but you are free to calculate the wavelength and then do that. So I'm just going to sub that in here. So I'm going to have this equation CNL over DF. Ugly looking thing, but it should work for us. All right, so to find that distance, that x3 bright, So we have the speed of light, that 3 times 10 to the 8 meters per second. We have the fringe we're looking at. We're looking at the third fringe. We want this length here, or the distance between the slits on the screen, so that's the 2.50 meters. And then we're going to divide that by the distance between the slits. We're told that's 1.67 times 10 to the minus 4 meters. And then lastly, we want the frequency of this light, which is 5.50 times 10 to the 14 hertz. So we got a lot of things in here. We want to make sure that we input this in the calculator very carefully. We don't want to make any careless mistakes. And because we have more than one number in the denominator, make sure that we bracket the entire denominator. Very important. So if I do all this, I'm going to get about 0.024496 meters. I'm just taking some extra sig digs for the moment. What this means is that that distance between the central maximum and this third bright fringe, that's about 2.45 centimeters. So we found that. We want to look at the dark fringe now. So if we look at the dark fringe, so now we're going to look at n equals 5, and I'll put a little d there for dark. So this time we're going to want lambda equals xd, and then we want this n minus 1/2 L. So we got to be a bit more careful this time, because we want this for the dark fringe, or that destructive interference. So again, we're going to solve for x. So x is going to be this lambda n minus 1/2 L divided by d. Once again, for an EM wave, we can sub in lambda. We know that lambda is just going to be the frequency, it's just going to be the speed of light divided by the frequency. So I'm just going to kind of mark that here. So for an EM wave. So we have this equation, this x equals c times n minus 1/2 times L divided by df. Whew, nasty looking thing, but we can certainly get it done. So the fifth dark fringe, so we have our speed of light, still 3 times 10 to the 8 meters per second. We have our n minus 1/2, so we have our fifth fringe minus 1/2. We have our L of 2.50 meters, so we have our 1.67 times 10 to the minus 4 spacing between the slits. And then we have our 5.50 times 10 to the 14 hertz for our frequency. So a lot going on in this thing, but we can handle this. So if we're, again, really careful with the calculations, we're going to get that this is about 0.0367, I'll take some extra sig digs, 45 meters. Again, let's put this answer into context. What exactly does this mean? Well, what that's saying is that distance between the central maximum and this fifth dark fringe, this is about 3.67 centimeters. So the last thing to find the actual difference between, or to find the distance between the third bright and the fifth dark fringe, we're just going to subtract these two. So that difference, so we're going to take the fifth dark and we're going to subtract off of it from the, we're going to subtract the third bright off of it. So let's do that really quickly. So I'm going to recall previous answers in my calculator, and now I'm going to actually start to care a little bit about sig digs, so I want 3 sig digs at the end. So 0.122 meters. So what that's telling me here is that the distance between my third bright and my fifth dark band is about 0.0122 meters, or if you like centimeters in this case, you could say it's about 1.22 centimeters. So that's this question. So this is a nice little diffraction question, really takes up the thinking a bit. And then I just want to show you too how we deal with these dark fringes. So like how we use that in our equation. So I just want to tack on one little thing to the end of this example here. And just, this is another little piece of evidence that goes to the whole idea of the wave model of light. So when Young proposed his experiment, he, and the evidence with it, you know, a lot of people bought into it and said, yeah, light probably behaves like a wave. But of course you have your skeptics. They were saying like, well, do you have more evidence? Like they want it more, like they didn't have enough. So what was actually proposed was by this gentleman named Augustin Fresnel. He proposed a mathematical wave theory, and another French mathematician, Simeon Poisson, he argued that from Fresnel's theory predicted that if we had light shining on a disk, in the shadow of that disk, there should be a bright spot. That's what was predicted in Fresnel's equations, and that's what Poisson had argued. Now, Poisson had actually tried to show the existence of this spot, but he actually didn't find it. And he was actually happy with this. He kind of came in with a bias. Poisson was a real big fan of the particle model of light, and he actually contributed to it as well. So he had an incentive to try and, disprove this bright spot in the shadow. Eventually, the experiment was redone by a gentleman named Dominique Arago, and he found that bright spot. And this bright spot here could only be explained by wave theory. If we were dealing with particle theory, the particle theory would say, okay, once light hits this disk, the rest of the light would travel in a rectilinear manner, so travel in straight lines. It'd be bypassing this shadow, so we wouldn't have a dot in the center. By showing the existence of that dot, or by showing experimentally, this gave even more evidence to the wave model of light. So we're just racking up the evidence for this. So Arago was the one who experimentally discovered the spot, so you will hear it referred to as Arago's bright spot. Sometimes you'll see it referred to as Poisson's bright spot. Some people say, and whether this is true or not, that they named it that sort of as in a mocking way to Poisson, like he was so adamant that it didn't exist, but that it did, so they want to kind of tie his name to that forever. Whether that's true or not, we don't know, but as you've learned, physics and science in general is full of all those cute little stories.